last speaker of the morning mini course session, again, needs no introduction, and in fact has already been introduced by various slides, especially what Nick was showing. I can't give an introduction that's much better than crediting him with the most beautiful picture in all of astrophysics. So Paul Goldsmith has obviously worked a lot on the science observationally that we're going to be talking about, in particular recently as the project scientist for Herschel. But he's also one of the people that makes all these observations actually possible, currently as the chief technologist for astronomy, physics, and space technology director at JPL, which is a very narrow purview, clearly. And he's going to tell us about basically what's happening today and hopefully in the near future in the observational opportunities. Thank you.
Thank you very much. Well, thank you all for hanging in here as we approach lunchtime. It's a challenge to give this review simply because it would be somewhat boring to just enumerate lists of telescopes or instruments. And yet there's a huge number, and it's a very exciting time because there is a kind of shift going on, for better or worse, as I'll mention, in what's available for astronomers. We've heard a lot. We've heard about string theory. We've heard about observations and the importance of connecting those two. And so advancing the observational knowledge about star formation is really what I'm going to talk about. And so I've decided the way to do it, just to organize things on the size scale at which we're talking about observations, rather than by wavelength or by something else, to sort of review some of the things at least I'd like to observe about star formation and be a little bit eclectic in that. So you'll excuse me if I don't cover everything, but there's more room for discussion on this as well as the more scientific talks. Well, what about stars, eh? I mean, if you're going to study star formation, some of you might want to actually study stars. That is obviously something that's obviously goes way back in astronomy. There's nothing new. But of course, we now have the capability of integrating both ground-based and space-based facilities for studying stars. Some of us may be old enough to remember when people used the so-called Palomar-Schmidt images of stars. They're now, of course, much better, deeper catalogs, and many more to come with LSST. There's Hubble, there's the infrared space missions, Herschel, and Spitzer and IRAS. And of course, on the ground, we have JWS ALMA and JWST on the ground, but hopefully by 2018 going into orbit. That's going to be a big deal, at least from my perspective, if they really ever get that launched and operating, because then there will be other missions that can be talked about, such as WFIRST, that will also be relevant for studying star formation. So in contrast to the days when the sort of famous ground-based observatories were built to study stars, when they thought you would only do that in the visible, of course, we now know if you want to study star formation, you really are talking about stars that are kind of immature, right? They haven't quite grown up, so they have envelopes and disks. And of course, the disk and the dust in the disk being heated somewhat by the starlight is cooler, and so instead of radiating in the visible, as shown by the blue curve for a star, goes way out through the infrared and even into the submillimeters. We've heard about tracing the mass through this optically thin part of the disk. So the big difference in studying stars, especially young stars, is you really need this kind of multiple or multi-wavelength approach to know what's going on. This nice diagram shows what you could get with a star, a disk, and an envelope with the different parts adding up, and you can see you sort of, if you want to study the envelope, you really have to be out at the longer wavelengths, and you have the absorptions from the dust closer to the star, etc. So all this means is you people who want to observe have to think in one paper, if you're studying one system, combining the data from many different facilities. And of course, this one virtue of this recent space missions, at least, is the data are relatively easily available to you in archives. Certainly Spitzer and Herschel. I'm not so sure about the JCMT, but that's a different, not a space mission. And so you can try to put together things like this if you're studying a star. And you might want to do this, for example, for doing things like adding up the number of young stars in a region and seeing how the stellar mass compares to the gas mass. We've heard Nick's caveats about that but of course, the more multi-wavelength data you have, the better you can try to figure out the mass of each individual protostar. And in this work, studying these in Perseus, Amanda Heiderman et al. Actually got this relationship between the gas density and the star formation rate, the standard solar masses per year per square kiloparsec, which does not actually agree with some of the more larger scale things. So it's a question of scale. And to do this, you really have to deal at some point with adding up the masses of individual stars. If you want to back off a little bit and you say, so where are these stars forming? They're mostly forming in dense cores. As we heard, these condensations of gas and dust at roughly 10 Kelvin, heated mostly by cosmic rays and a little bit by the external radiation field. This is a Herschel map of one part of Taurus in which you see these dust emission. And then down here is an ammonia map from Seo, Shirley, and others, where you can again see that most of these dense cores, you see the gas adding up. Now, of course, there are big arguments these days about what's the right tracer. The dust has a certain pleasant nature in that you don't have to really deal with chemistry, but the more people look carefully at dust spectra, to my mind, the more they see that there is no one model for dust grains that will fit all the data. So that you may find, for example, that in these highly filamentary structures, the dust grains in the outer parts are different from the dust grains in the inner parts, so that getting from the emission to the mass is not so trivial. In this and subsequent slides, I'm going to try to connect the observational capabilities by showing you pictures of the relevant instruments. So I won't always recite their names. This is, of course, the Green Bank telescope that is a terrific instrument for studying ammonia at roughly a 1.3 centimeters wavelength. They have a nice focal plane array on it, so you can actually map large regions and try to get the mass of gas there, albeit with the certain caveats as well. Now, I think Jonathan already showed this slide, but one of the things we certainly would like to observe is the magnetic field in star-forming regions. Can't find anything more controversial than that about what the importance of of the magnetic field. And in this case, I'll point out this paper that is just being published was entirely based on archival data. That is, people had actually done projects of doing polarimetry of these two clouds and just left them in the archives, never published. So you don't even have to do anything, so to speak, except know how to access the archives. Well, it's not so simple because it turns out the data had some problems that had to be re-reduced. And anyway, this was from the JCMT. The CSO has, I think, some also unanalyzed polarimetric data. And this in the submillimeter, a moment's glance will, I think, make you agree that this magnetic field, as indicated by these lines, is highly ordered. That means it must be dynamically significant. And indeed, I think Jonathan already showed this, what went by so fast. Basically, it's saying that these clouds, the magnetic field energy is comparable to gravitational potential energy that's strong enough to do things like suppress fragmentation. Well, magnetic field work is from the JCMT may continue because they are planning to commission a new polarimeter with a Scuba 2 array that will be far more powerful than that available previously. Another important opportunity will be SOFIA. Darren Dowell, who's here or there, is the PI for a new instrument called Hawk Plus, which was a polarimeter that will fly on SOFIA, covering the range of roughly 50 to 200 microns. That's the peak of the dust emission from GMCs, at least, a little bit short wavelength for colder clouds. But compared to what could be done in the past, when you got maps like this, it will be vastly more sensitive and be able to, in a single sort of footprint, because of the large format detectors, get polarization data for large chunks of clouds at a single time. And with this screen cut off, I think it's trying to say that there should be put on SOFIA in August of 2015. That's next summer, and hopefully be available thereafter. So for those of you who want to get involved in that question, there is opportunity. Another way to study the magnetic field is through the measurements of the Zeeman effect. The infrared polarization direction that you get from the dust grains says nothing directly about the magnitude of the magnetic field. That was inferred by the assumption that the Chandrasekhar-Fermi method is relevant, and it probably is, although there are uncertainties. For a direct measurement of the line of sight component of the magnetic field, nothing beats the Zeeman effect, and there's some really nice millimeter molecules just waiting for people with a lot of determination to go observe them. The CN molecule has a nice substantial G factor, and this is a spectrum of CN, and this is the V spectrum fit to a magnetic field of 1.1 milligauss. Well, it fits pretty well. It's certainly not 10 microgauss, and it's not a Gauss, but whether it's 1 milligauss or 2, you could argue. Nevertheless, this is vastly important to get these numbers even pinned down. There are only a handful of Zeeman measurements of dense clouds. There are more of somewhat less dense clouds done through OH. This was done at the IRAM 30-meter telescope in Spain. That has a very nice polarimetric system for doing CN. Hopefully someday there will be other facilities that will also do that. For example, if you want to go back to doing OH, which is an interesting Zeeman molecule, you can use Arecibo, still operating and available with a nice polarimetric system. ALMA, although I don't know if it's available just yet, will surely have that capability in the near future. So again, these arguments about the magnetic field need not go on forever if somebody takes the trouble to do the difficult observations. All right, so moving outwards, where are these dense cores and where do we find them? Well, although Nick alluded to it, I think in my mind, one of the most striking discoveries in the galactic ISM from Herschel was the fact of the prevalence of these linear filamentary structures that you see once you have the large scale but high resolution dust emission. So these different groups, mostly, this is Orion, I think. No, DR21, I'm sorry, this is Long Ridge. And all these other clouds, too, by Herschel were shown to have filamentary structure. And if you like image processing, you can enhance the filamentariness. That's sort of what the Karma image did all by itself, since it had only the interferometric visibilities and no single dish. And it was found that, again, that these filaments can be broken up into those that exceed a threshold of stability and those that therefore become unstable for fragmentation, and those that are stable. And the white here shows the parts that are susceptible to fragmentation, and the blue are the cores that are identified as shown in this blow-up of this one region. So here are all these cores that are forming in the white, that is unstable parts of the filaments. And here again, if you want to study filaments, you need to be able to map substantial areas with good contrast, but SOFIA can do that. ALMA, certainly if you can get a lot of time in mosaic it, but single dish telescopes are probably the more important in the near term. That is the GBT, IRAM, and soon the LMT, the large millimeter telescope, the UMass Mexican instrument near Puebla. Well, so these filaments are found of all molecular clouds of all types and sizes. This is again Taurus with the CO integrated intensity and backdrop, but the colors are the filaments identified by Gina Panopoulou and our collaborators using some nice software that's been developed from this. So you can, if you can get your hands on data for molecular clouds, you too, if you can take advantage of one of these newly developed software packages, can analyze their filamentariness and get the mass per unit column density, look at whether these are velocity coherent. Again, you need to have the tools, and for that, I think the 12CO and 13CO are the most important. 12CO, as we've heard, as you know, is optically thick. It's a good tracer of the general cloud material and particularly sensitive to disruptions from outflows and things like that. 13CO is optically thin or not far from it, and it's a relatively faithful tracer of the mass column density. You've got to watch out about depletion at low temperatures. So how are you going to map these clouds and find those filaments and those cores? Well, you want to do spectral line imaging of molecular clouds. And to do things like get these nice maps, you have to have a lot of pixels in your map, which is another term that Mark Heyer came up with spatial dynamic range. In other words, you need a map that's much larger, many times your angular resolution, not 10 or 20 or 50, but 1,000, for example. And to do that, you're going to have to spend either your whole life or you have to have a focal plane array. Now, fortunately, technology is maturing to the point where now pretty much every large single dish radio telescope is equipped with focal plane arrays. The maps of Taurus you've seen and generously praised were done with a Sequoia array, which had 32 pixels. To my mind, a sad testimony to the state of astronomy in the United States that Sequoia is going to become a 16-pixel array because 16 pixels were sold to another country to pay for keeping it operating. And so it will be a 16-pixel array and will be on the 50-meter LMT telescope in the next fall. Argus is a 16-pixel array developed by Lorene Samoska here and others at Caltech, JPL, and Stanford. It will be put on the GBT this coming spring and will make the GBT capable of mapping CO in molecular clouds with an angular resolution of about 6 arc seconds and enormously faster than with an interferometer because of the huge collecting area. Bears is a 25-pixel array, similar frequency range on the Nobayama telescope, and Hera an 18-pixel array for the CO 2-to-1 and related lines on the IRAM. So all of these things mean that these telescopes, not this one, it's gone, but the others will be able to do much faster large-scale mapping of molecular clouds and let us understand how universal those filaments are. Well, everyone here seems to have had a slight tendency to talk about their own work, so I won't break that. This is a map, for example, of Taurus, not so often shown because this is in the 12CO integrated intensity. But it reminds you that even 12CO, despite all these aspersions on its character of being optically thick and thermalized and therefore not capable of telling you any information at all, really gives you a pretty fair idea of the appearance of the cloud. The lines here are the magnetic field directions as inferred from, mostly from optical polarimetry. And you can see that in the bulk of the cloud, the field lines don't seem to have anything to do in detail with the structure seen, but in the diffuse parts, you do see all these filamentary structure here, a different type of filamentary structure, aligned with the field lines. And of course, the kind of thing that people are therefore interested in doing is this mass accretion of this more diffuse CO onto the main molecular cloud. If you switch to 13CO, you do see a more concentrated structure, and now you really see the filaments that we saw before in the infrared. These are the kind of things that are traced and have the star formation threshold in them, in particular this long filament here. So what is going on inside molecular clouds? Well, I'm not going to argue that we understand it, but we certainly are pretty sure that supersonic turbulence is agreed to be present, and even in relatively quiescent clouds like Taurus, all except the very small centers of the dense cores. But the problem is that the supersonic turbulence is generally agreed now by theorists that it will dissipate in a relatively short time, much shorter than you want these clouds to last. So one of the, to my mind, important theoretical question is what regenerates the turbulence that you see, observe in molecular clouds? It could be internal or it could be external, Pache-Nick's statement. And so there could be, for example, it could be the feedback from star formation. But it's a little bit strange. I mean, I'll show this slide again. It's not bad, right? Taurus has about 250 YSOs in it, which are all WIMPs. There's not a single B star associated with Taurus. It's a little hard to understand exactly how it could be the star formation that's regenerating the turbulence here. Other theories are that turbulence is coming by mass, is being regenerated by the energy dissipated by mass accretion. I mentioned before these filaments here, and in fact they're quite elaborate theoretical models of the mass falling into the potential well of this molecular cloud, or its brothers and sisters, being responsible for that by Goldbaum et al. So we have to be, I think, finding that source of the regenerating turbulence is important. Where do these clouds come from? Well, I've talked about the atomic molecular transition. Adam mentioned a lot more about this, and the question of, do these clouds come from atomic gas, or are they sort of reformed from diffuse molecular gas? This is going to be a very fruitful area of research, I think. And I think that here, to do these nearby galaxies, we have the VLA for the H1. The CO will require combinations of single dish and interferometers. It'll be a challenge for ALMA to mosaic highly enough to do that. Perfect for KARMA, but which may not be with us. So I think this will be interesting to see how observers manage to get the resolution they need over the not insubstantial fields of view to study this question of the origin of molecular clouds. Another way that's been probed is to use the C+ line, which with Herschel became really nicely accessible, and the GOT-C+ project led by Bill Langer at JPL did a kind of first survey of the Milky Way, just a few hundred lines of sight, but spread around the whole disk. So no images of clouds. The C+, but the difference is for the first time you had velocity resolved spectra. That's you had a heterodyne system, and you could place an individual feature at a kinematic distance, and so you could do things like measure the galactocentric variation in the C+ emission, and you could study, for example, whether it correlated with H1 or whether it correlated with CO. And in fact, one of the nicest results from this study was that it confirmed the existence of this so-called CO dark H2 gas. That is gas primarily in the envelopes of molecular clouds where the hydrogen is still molecular because it self-shields, but the carbon is in the form of C+ rather than CO. So you cannot trace it with CO, you cannot trace it with H1. The first reference to this gas called it the dark gas. Now that was really confusing because after all, if it were dark gas, how could you see it, right? I mean, so, and it was not dark matter or dark energy. It was really just, it's dark in CO and it's primarily made of H2. Well, anyway, in this survey, the fraction of the molecular gas in this form was seen to rise from a very small level in the central part of the galaxy up to as high as 80% in the outer part of the galaxy. So that was consistent with, I think, one of the questions of what outer galaxy clouds are different than inner galaxy clouds in having this large amount of CO dark H2 around them. Recent paper by Jorge that he'll probably talk more about separately correlated the intensity from C plus with star formation rate. And so here you have individual galaxies. You have the Milky Way divided into rings in the GOT-C plus survey. Here's the whole Magellanic Cloud. Here's the whole Milky Way. And these are some nearby galaxies from Deleuze et al. Pretty good correlation over about 6 orders of magnitude. May not be perfect when you get into starbursts and weird galaxies, but you get pretty good data. So how are we going to do this? Herschel, unfortunately, is now been put in what ESA, I thought, very ungenerously called a solar disposal orbit, which meant that it's in orbit around the sun, going sort of around on the Earth. In a few hundred years, it may come back, but we probably will have lost interest by then. So if you want to observe C+, one of the few opportunities really now is through the NASA balloon program. And in fact, Chris Walker at the University of Arizona is the PI on a balloon project called STO2, which is supposed to launch in 2015 from the Antarctic and will map the inner galaxy. So this will be the first time you get, hopefully, images of the C+ emission. That is three-dimensional, 2 spatial, and 1 velocity image of C+, albeit only with 1 arc-minute resolution. Well, okay, when we're talking about where clouds, molecular clouds come from, you might think, well, do they come from the atomic gas? Well, this is a map of a region of the galaxy done with Arecibo in H1. And the galactic plane is sort of up here, and this is a kind of spur sticking down. Well, if you put the molecular part of Taurus on this map, it sticks there. Doesn't have a real obvious connection, does it? It'd be a pretty hard place to figure out exactly which H1 gas was converted into molecular gas to make this baby. And in fact, it may have nothing at all to do with it. Other studies are somewhat less pessimistic. A recent study by Lee, Stanoverovich, Douglas, and their collaborators of the Perseus region showed here is the H1, here is the CO and 2 micron emission. Well, they sort of have some relationship, but it's awful hard to really, they find that basically the H1 is constant over the whole region of this molecular gas, but that once you get above about 10 to the 21st per square centimeter, you start building up the molecular component. So it's like it sits on top, this molecular sits on top in Perseus. I don't think you could really make it, doesn't seem obvious that that's the case in Taurus. So this again, comparing the H1 and the CO can, as I said, be done. Use Arecibo, use some millimeter telescope, and you're in business. All right, well, I'm getting towards the end here, I hope, yes. And we'll talk about energetics. After all, you want to know, what does star formation do to these molecular clouds? Well, one way, of course, is to look at the dust. And if you have a bunch of wavelengths, like with Herschel, you could get a spectrum of the dust emission and fit a dust temperature. And with the dust opacity, you can sort of calculate the infrared luminosity. This was actually done and fitted, and this is the case of SAGE B2, big cloud near the galactic center. And these Estelud et al. Found dust temperatures between 20 and 30 degrees. You can do the same thing fitting a whole series of CO lines. and you can get the gas temperature, which turns out between 100 and 300 degrees. Clearly not coupled. There's no rule that says they have to be. And in fact, at the densities that you get here, it's quite reasonable. They're not high enough to couple the two. But again, the gas only radiates a tiny amount of energy compared to the dust. But energetically wise, it's very interesting to figure what's heating this gas to such much higher temperature than the dust. To do that, again, we no longer have Herschel, but you will have SOFIA. The photometer instruments on SOFIA will get some of this wavelength range. And there is the prospect, perhaps, of a next generation space mission called SPICA, which is being led by the Japanese Space Agency in collaboration with SRON in the Netherlands, that will have an instrument sort of like Spire on Herschel, and will be able to do this beautifully, much better. Another way we heard very briefly mentioned is if you want to think about how star formation puts energy into these clouds, you have this classic bipolar outflow driven by some kind of magnetic twist from the disk and a young star. Obviously, if you're driving stuff out, it's mostly ionized gas, but it sweeps up molecular gas, and then this part of it, this lobe would be red shifted and this blue shifted, so you get the famous bipolar red-blue separation. And from the shifts in velocity and the mass, you can calculate the energy input. Nobody has yet shown convincingly that the energy from bipolar outflows is really enough to maintain the turbulence in interstellar clouds, but they've tried really hard. On the other hand, there may be other things than outflows. For example, in a recent paper, Arce and collaborators were talking not about outflows, but about shells. That is, you see regions in clouds where you have hollows surrounded by a little extra column density. These have sort of been excavated by a young star, an older young star there. And so therefore, it's a way, the bipolar outflows are sort of 10,000 years kind of scale. These shells may be that old or older, so you're looking at a sort of previous generation of stars, and you have to get the mass and the velocity shifts. In this case, Arce et al. Claimed that the energy in these shells was very substantial compared to the turbulent energy in this cloud. So it's intriguing, not accepted by everybody. Again, observationally, go get yourself maps as high velocity resolution, look for these velocity shifts, and try to get the morphology right. Nobody, I think, yet has a patented shell identifier code. I mean, filaments, yes, outflows, yes, but not yet shells, but that could be coming next. When we move a little further out, there have been now nice studies of nearby galaxies in great detail. A recent work by here in M31 by Maria Karska and her collaborators mapped these regions with Herschel, and they're actually, in this case, with C+, and they're looking here at this famous C+ to infrared, total infrared ratio, which increases very dramatically as a function of galactocentric distance, as was heard a little bit about also earlier. This kind of work in nearby galaxies was just enabled really with Herschel, and it will be continued with SOFIA. There's a new instrument coming on SOFIA called UpGrade, which will be, actually, this isn't quite fair, it's 7 pixels, but each with 2 polarizations. So it really is the equivalent of 14 pixels. You get about 15 arc-second beam, pretty nice for studying nearby galaxies. And again, there are also balloons, as I mentioned earlier, with a bigger beam. So C+ is doable. Moving to external galaxies, of course, with Herschel, we had all kinds of beautiful spectra. If you have to add the long wavelengths from the ground-based. And it's a challenge to do this because, in fact, if you look carefully here, these dotted lines indicate that they have to fit several different temperature components to get the total dust emission. So you need the full spectral range. You're likely to miss one of them. Similarly, you can do the same thing with CO. If you get a whole set of CO lines, you can try to fit these spectra. That's proving to be quite productive, but it's going to be difficult. ALMA will give you some of these, but only when you can fall in the atmospheric window. But we may be saved by the fact that if you really go to the distant universe, here's a spectrum of a galaxy HFLS3 at Z of 6.3. The thing that you realize here is that to do all these things now, the observations are at a completely different wavelength than you're used to thinking them as. I mean, if you're talking about C plus at 158 microns, rest wavelength at Z of 6, you're talking about 2 millimeters. So you can do it with ALMA, for example. And things that you think of as like the millimeter CO lines that you could do with ALMA, really you end up doing with the VLA. So it's, I mean, big redshifts may make things difficult to detect, but they move the lines into a completely different range of the spectra. On the other hand, if you want to stick with the galaxy, as I mentioned, there's these balloon opportunities. This STO2 mission will not only map C+, it'll also map N+, and the fine structure line of atomic oxygen at 4.7 terahertz. There are even more ambitious balloons being considered. This is supported by a NASA innovation program, which is talking about a spherical balloon 20 meters in diameter, of which you'd illuminate, say, 10 meters of it and have a 10-meter telescope above the atmosphere. People have not given up on future space missions. There are at least 3 that are very relevant to star formation that you may hear about in the next few years as we approach the decadal survey. There is the Japanese S-RAN Spica, which is sort of like a frigid Herschel. That is, it's the same telescope as Herschel, but cooled to 4 Kelvin. So the thermal emission from the telescope is reduced by about a factor of 10,000. And so is the sensitivity with the detectors they hope to have. This mission is somewhat problematic right now in terms of the politics, but it may yet happen. The Russians have a concept for a 10-meter diameter deployable telescope cooled to 6 Kelvin. It's quite ambitious. That would have go to wavelengths as short as 50 microns. A Spica would go to even shorter wavelengths. And there was previously a NASA concept called Sapphire, which then became Callisto, which was, again, cooled to 4 Kelvin. Again, the whole thrust here is to do sensitive photometry. You need to cool your telescope. That makes all these missions rather challenging and expensive, and we'll have to see which of them are there for you for the next decade. So there is a rich variety of instruments. Some are no longer operational. Herschel has gone for lack of cryogen. Others have been closed due to budget cuts. Some are being threatened. The Karma interferometer, Spitzer barely survived the most recent senior review, but is being funded for the next 3 years. The GBT is threatened due to lack of funding for NRAO. On the other hand, there are new facilities, ALMA in particular, hugely important. SOFIA, I think, will have an impact, especially with the new instruments being developed. And then, of course, you have JWST coming, and there are balloon missions, and the future, I don't know. So you win some, we hope. We're losing some, but on the balance, I think it's an exciting time for observing. So thank you for your attention.